continuing our discussion on coordinate geometry, we need to focus more on graphing equations. Now, you're pre-calculus students now, so see there's sort of this mental jump in thinking that eventually occurs with you as you go from an algebra student to a pre-calculus student. Kind of like the same mental jump you had to make in going from an arithmetic student to being an algebra student. You had to sort of broaden the way you think about things, and you had to sort of accept new ideas and conceptualize things a little more readily. See, whenever you see an equation like this, it can be kind of intimidating. I mean, I have no idea what this graph looks like, but some analysis that you need to be able to develop as a pre-calculus student is understanding that this is a mathematical sentence that tells me something that's true for all the points that are on the graph. So see, when you pick a point at random, see, this is just a point I chose, 2, -1. Is this point on the graph of that equation? Well, this isn't something we can graph on the calculator, and we probably have to get some advanced software or an app on my tablet to actually graph this out. But if I want to check and see if a particular point's on the graph, then the one broadening of your conceptualization for equations like this is to realize that, you know, this is something that's true for every xy coordinate that's on this graph. So you can take a point that you're proposing to be on that graph, plug in the x value for x and plug in the y value for y, and see if it does generate that something that equals 13. So we're going to check this out for this coordinate. X equals 2, y equals -1, and I want to plug that carefully using the order of operations into this equation. So the equation says x gets squared first, so that'll become, replace my x with 2, so that'll be 2 squared, minus 4 times x times y, so I'm replacing x and y for there, and then plus y squared plus -1 squared. Does this give me, or does this equal, so question mark, 13? So your work is to simplify the left-hand side after making those replacements for x and y carefully with the order of operations. So exponents get done first. That becomes 4 minus 4 times 2 times -1. Now this is -1 being squared, so there's no sign change. Well, the -1 goes away, but it doesn't affect the plus in front. That'll still be a +1. So exponents are done. Now you want to do the multiplication in the middle. That's going to be 4 minus 4 times 2 is 8. 8 times -1 is -8. And then add left to right. 4 minus -8 is going to be 4 plus 8. That'll be 12. 12 plus 1 is 13. And according to the mathematical sentence up here, any point that's on this equation's graph has to have the xy coordinate going through this calculation and equaling 13. And since it does, that means this is a point on the graph. So I guess the answer will be yes. Determine whether the given points are on the graph of the equation. Yes, the point is on the graph. So same idea with this one. You want to start with a fresh copy of your equation, plug in x equals -2, and plug in y equals +1, and see if it gives you a true statement. See if it returns the 13 like the equation says it should. So x squared, that's going to become -2 squared, minus 4 times -2 for x, -1 for y, plus -1 squared for y. Does this equal 13? So just be careful with your order of operations. Do your exponents first. -2 squared will be a 4. -1 squared will be a +1, so that'll keep that plus in front. And then do your multiplication in the middle. 4 times -2 is -8. -8 times -1 is back to +8. So notice, your subtraction here is not going to change. In other words, those two negatives multiply and cancel each other out, so this negative stays negative, unlike what happened over here. You had the minus negative becoming positive. And then the +1 comes down. So now you add and subtract left to right. That's going to give you -4. -4 plus 1 is -3. Negative 3 does not equal positive 13. So this point is not on the graph of the equation. Okay, so a simple yes or no after showing your work and tallying whether the point satisfies the equation or not. Okay, now a more systematic way of actually building the graph, it will be very difficult to just pick points at random and plug them in to see which one give you true statements or not, because unfortunately there are an infinite number of points on graph paper, and not all of them nice integer points like this either. You've got to consider, you know, rational values with decimals or even irrational numbers in some cases. So a more practical way of generating a graph is just to analyze it by making a table of values. Okay, now yes, you have a graphing calculator that can make a table of values for you, but I need to assess your ability to be able to build this table from your mathematical thinking. So we're making a table of values for the graph of the equation y equals absolute value of x plus 2. So based on the way the equation is set up, y is defined in terms of x. It's best to probably just pick some values of x and plug them in and see what the y values are that go with it. So maybe a few negative x's, 0, and then a few, well, I'll go ahead and extend my table, a few positive x's. Okay, go ahead and make my extra row entries down here. Okay, and so then we'll get corresponding y coordinates that we can actually plot on the grid to see what the equation is going to look like overall. Okay, so when I plug in negative 3, you're plugging negative 3 in for x. The order of operations is to do the absolute value of negative 3 plus 2, which is going to be the absolute value of negative 1. So when you plug in the x and you get a y coordinate back, this makes a coordinate pair, negative 3 for x, positive 1 for y, that you can assert is definitely on the graph of the equation. I know for certain that coordinate, negative 3, positive 1, is on this equation's graph. So now plugging in negative 2 for x, take a fresh copy of your equation, plug negative 2 in for x, and that tells you y equals negative 2 plus 2 in absolute value. So that's going to be the absolute value of 0. So negative 2 for x, 0 for y, that's an x-intercept. This graph crosses the x-axis at the value negative 2 for x. Okay. Now just keep going. Finish your table of values. Maybe eventually you'll establish a pattern and you can kind of assert what the rest of the pattern is going to look like. When I plug in negative 1 for x plus 2 in absolute value, that becomes the absolute value of positive 1. So we get the same output here that we got at negative 3. This means the coordinate negative 1 for x, positive 1 for y is on the graph. So far, the graph is making a sort of a bounce shape. When I plug in 0 for x, you're taking the absolute value of 2. So at x equals 0, y equals 2, you have a y-intercept right there. I think there is a pattern emerging because now for every value of x that you're plugging in past the negative 2, you're going to have to add the 2 to it and then take an absolute value that's always going to give you a positive number. See, when you plug in 1, you're taking the absolute value of 1 plus 2, which is 3. So your y values are going up one at a time for every x value that you go to the right. So x equals 1 gives you y equals 3. X equals 2, therefore, will most likely give you y equals 4. X equals 3 will most likely give you y equals 5. And double check it if you think I'm crazy. When you plug in 3 plus 2 is 5, absolute value is 5. So see, if you look at the table of values and consider the calculations you've done, sometimes the calculation lends itself to a pattern to help you get the graph. So far the graph looks like a big check mark. But what you got to keep in mind is there are values of x further left and right of just the few values that we chose here. Say, for example, if I want one further, some point further to the left of negative 3, like maybe, let's say I wanted to do negative 7. Y would equal the absolute value of negative 7 plus 2. So see, that becomes the absolute value of negative 5, which is positive 5. So that means that x equals negative 7. 3, 4, 5, 6, 7. I'm going to go 1, 2, 3, 4, 5. So this graph is making some kind of giant V shape. So let me get my straight edge out, connect the dots as best I can, comes down here, makes a right angle turn at that x-intercept, and then keeps on going upward in this direction. So the full graph of something involving absolute value kind of makes this hard V shape. Okay? And that's just one example. I mean, just making a table of values helps you to assimilate what that equation says about how its graph is. You can kind of start to build patterns and see trends in how certain equations generate certain kinds of shapes, like the absolute value shape is this V shape, or a squared x gives you a parabola, or different associations like that. That's the kind of conceptualization you're going to have to do as a pre-calculus student going forward, is to let these graphs kind of start to speak to you in a good way, so that you can get a mental catalog of what their shapes look like and be able to refer to them pretty readily. Okay. One more thing I want to talk about before we venture forth into equations of circles is just finding intercepts again. I mean, that's going to be a pretty paramount skill used throughout calculus, is using the intercepts for certain analysis that you want to do in mathematics. So a reminder, x-intercepts are found by setting y equal to 0. So I get x-intercepts, set y equal to 0. So that means the equation becomes 0 equals the square root of 36 minus x squared. And then I need to solve this equation for x. Okay, so x-intercepts are found by setting y equal to 0, solving for x. This generates an x that's inside of a radical, so you can go ahead and square both sides, since now you're solving this as an equation. And then if 36 minus x squared equals 0, that means x squared equals 36. So, well, go and finish the equation solving process. The square root gives you x equals plus and minus 6. So that means your x-intercepts are at positive and negative 6, 0. So whatever this graph looks like, it crosses the x-axis at positive and negative 6. Okay, if I plug in 6 and negative 6 for x, it gives me a 0 value of y, and that constitutes an x-intercept. Okay, y-intercept, remember that's when you set x equal to 0. So take a fresh copy of your equation. Every use of x defaults to 0. So y equals the square root of 36 minus 0 squared. So y-intercepts usually are a little bit easier to find. Y equals the square root of 36. Now be careful. This square root was already here, so there's no plus or minus in front of it. This square root that we took here was because we had to take a square root to solve for x squared. Remember, if you take the square root to solve for a variable, you have to remember the plus or minus. If the square root's already in the equation, no plus or minus is needed. So that means the correct y-intercept is positive 6 only. So that means you'll cross the y-axis at a y-intercept at 0, positive 6. So whatever this graph looks like, it hits the x-axis at plus and minus 6, looking something like this, negative 6 and positive 6 for x, but it only crosses the y-axis at positive 6. So we know for certain those are points on the graph, but without any other knowledge about the equation, or maybe even some other kind of analysis, that's the best the intercepts will tell us. Just gives us a rough idea of a few points on the graph. Okay.